Normally, when we talk about optimization, we see it as a calculus problem. We take the first derivative of a function and then we find our zeros. And it sounds pretty easy, but there are some problems with that. One of the good things about it is that you always get perfect answers and you don't always need a computer, if the function's simple enough. But the thing is that you require to have symbolic manipulation, and that can be hard on a computer computationally, and it can be hard if you're doing it on paper. It also requires the existence of either a regression line or a known function. And that can be really hard if you have a relation that is either random or stochastic or isn't really qualified as a function because it doesn't pass that vertical line test. The thing is, though, is that we can see optimization from a completely different perspective, not involving calculus at all, but simply a guess and check, but really fancy guess and check way. So you see I have my stochastic relation here. That was poorly drawn in GIMP using the airbrush tool. And I'm going to act like I'm a computer. It requires a guess here. So I'm going to say that my local maxima is here. Yeah, it's a pretty poor guess, but imagine I'm really stupid. And it works if you're really stupid. So first, I'm going to go left on my function. Okay, I'm going to act like I'm down here. Oh no, I've gone downwards. So I'm going to go back here. I'm going to go back up in this direction. And I'm going to end up around here. Well, I've noticed I've gone upwards. So I'm going to keep going up. I'm going to keep going up here. Oh, I've gone even further upwards. Well, what if I keep going? All right, slightly further upwards. Then keep going. Oh, and I've noticed that I've started to go down. Well, that means I've probably passed the maxima. So I keep going back. So I go back here. And I notice, okay, I went back up. And now the computer is in this sort of game where it sort of keeps going back and forth and back and forth and back and forth until it reaches that local maxima region. And that'll work too if you wanted to find, your minima down here or your minima down here as well. Any extrema works like this. It works going back and forth. And the more iterations you have, the more accurate you can be. You can never, however, get the perfect answer that we were talking about before, but you can get an answer that is within enough significant figures for it to matter. So, how does this work in MATLAB? I'm going to take away GIMP here, open up MATLAB, and I'm also going to open up a notepad file called untitled. Don't want to simply type all this time and waste your time. First, we're going to define a object called f, and it is going to be a function of x and y, and it is going to be this nice looking function here. Probably want to see what that looks like, so we're going to use fsurf to graph it, and this is what it looks like. It's pretty nice looking. We're going to need this to take our guess for it to work. And, we're going to be stupid again to show that this works. And we're going to say it's like negative 0.5. Yeah, because that's what I wrote in my notepad file. And that's also just a good demonstration. So we're going to minimize that. We have a pretty good picture of what this looks like here. We're trying to find local minima. That's what I've decided via the untitled notepad. And so we're going to create another object called fun, because math is fun. Wow, I can't believe I said that. And then we're also going to include our guess. Okay, so we're going to define this little point here, and it's basically just going to be this two-dimensional array that is the x and y values, and it's just going to be there, and it's going to be a part of our min function that we see later on. Then we're going to then select the type of algorithm that we use. So this is going to define the decision making of the computer, as I was talking about before, going back and forth, understanding where it's going. Then we're going to make it so that it displays our iterations. And this is important because we want to show how efficient it is. Then we instantiate this set of arrays using the fmin unc method. As you can see, we now have 6 iterations shown here, and we have some information that's shown based on what we put in this array. So it shows us our function values, our f of x values, shows us our step size, and it also shows us this thing called first order optimality. It's pretty weird. So what this is it's essentially using the gradient, and it's able to calculate the slope, what is essentially the slope, the gradient, the surface equivalent of the slope, and it is showing how much smaller it is getting over time. And this is how the computer finds out, okay, I'm going to stop making iterations by basically saying, look at the gradient. It is so small, it is basically 0. And I'm just going to stop. And it reaches this tolerance level, this optimality tolerance, where it just says, yeah, I'm going to stop doing iterations. And as you can see here, not many iterations were done. It didn't take very long for it to go from our guess to finding the correctest answer that you probably want. There's not really much of a difference between 0.405237 and 0.405237. And when you have such a difference in gradient, but such a lack of a difference in your actual answer, in your actual function values, then you've probably known that you're reaching your answer. So if we want our x and y values, we can simply call on that. So we'll put that over here. And as you can see, we have our values for x and y. So what's our function value? This is our minima. We'll check that out. And there it is. It's right around where we thought it would be. If we go back to our figure, that looks about right. Yeah, that looks about right. I mean, it is right. I mean, it's a computer. If it wasn't right, this would, well, I probably have to take it back to Micro Center. Anyway, and then we can also see the efficiency in it because it counted the functions for us, and we can see that it counted about 18 times. So it had 18 function evaluations, and it had 6 iterations. And why there's a difference there in that it is exactly 1/3 of the function count is, and we can see the function count counting in this column here, is because it needed to calculate the gradient. And calculating the gradient symbolically, right, we know how to do that using that del operator. But just like how you could calculate the slope numerically using 2 points, you have that point slope form, and you got that slope formula, you can also calculate the gradient by taking 3 points on a surface and then creating a plane. And that is your pseudo gradient, much like you have your tangent line, you have your tangent plane. So that's why it has the 3 function counts per each iteration, much like how you'd have 2 function counts if we were using something that was a line and not a surface. Thank you for watching. I hope you all learned something today about not just the math, but also the computation and the alternative ways of coming to what is essentially the same answer. I hope this is educational. Have a good day.